In early 1945, off the coast of Japan, an American F4U Corsair was forced to ditch after experiencing engine failure during a combat mission. The pilot ejected just before the aircraft hit the cold waters of the Pacific. Within hours, Japanese patrol boats converged on the wreckage, recovering what would become one of the most significant intelligence finds of the war's final months. For almost 3 years, Japanese pilots had encountered the Corsair in the skies over the Solomon Islands, Rabaul, the Philippines, and even Japan's home islands. They had come to respect its speed, firepower, and rugged construction. However, they had never before had the opportunity to study an intact example of the aircraft up close, to measure it, test it, and fully grasp how far they had fallen behind. The story of Japan's encounter with the F4U Corsair is more than just the capture of an aircraft. It marks a pivotal moment in Japan's technological awakening, when its aviation experts realized the full extent of American industrial and engineering superiority. By examining the Corsair, they would learn profound lessons about manufacturing precision, materials science, and design philosophy, truths that shattered their assumptions about their own capabilities. The Corsair that the Japanese salvage teams recovered was the result of years of American fighter development. Originally designed in 1938 to meet the Navy's exacting standards, the F4U had evolved into one of the war's most formidable combat aircraft. Its distinctive inverted gull-wing design, powerful Pratt & Whitney R2800 double wasp engine, and remarkable performance capabilities made it instantly recognizable. More importantly, it represented what Japanese aviation struggled to achieve: a perfect balance of speed, firepower, range, and structural strength. The roots of the Corsair can be traced back to 1938. When the U.S. Navy's Bureau of Aeronautics requested a fighter capable of exceeding 400 Mach in level flight, a revolutionary specification at the time. When most fighters struggled to reach 350 mph, but the Navy demanded more than speed. They needed a complete aircraft package, low stalling speed for carrier operations, a range of 1,000 miles, heavy armament, and the ability to carry bombs. Chancevott's response was bold. Chief designer Rex Beisel and his team decided to build the aircraft around the largest, most powerful engine available, the Pratt & Whitney R2800 double wasp. This 18-cylinder, two-row radial engine produced 2,000 horsepower, nearly double that of most contemporary fighters. To accommodate this immense power, they designed a massive 13 ft4 in diameter propeller, the largest ever mounted on a fighter aircraft. The engineering challenge was how to provide clearance for such a large propeller while maintaining structural efficiency. For carrier operations, the solution became the Corsair's most distinctive feature, the inverted gull-wing design. Instead of the conventional straight wings, Beisel's team designed wings that angled downward from the fuselage before leveling out, forming a distinctive M shape when viewed from the front. This configuration allowed for shorter landing gear while still providing sufficient propeller clearance. The angle where the wings met the fuselage also created optimal aerodynamic conditions, reducing drag. The prototype XF4U-1 made its first flight on May 29, 1940. Piloted by Lyman Abulard Jr., the chief test pilot for Vought, from the company's factory airfield in Stratford, Connecticut. By October 1, 1940, during a test flight between Stratford and Hartford, on October 1, 1940, the XF4U-1 achieved a ground speed of 405 mph with tailwind assistance, making headlines as the first single-engine American fighter to reach such a milestone. The aircraft's actual maximum level flight speed was 378 mph at 23,500 feet. Still an impressive performance for 1940. By late 1942, production F4U-1 Corsairs began reaching operational units, with Marine Fighter Squadron 124, VMF 124, being the first to receive combat-ready aircraft. Deploying to Henderson Field on Guadalcanal on February 12, 1943. The Corsair's combat debut was less than auspicious. On February 14, 1943, during the infamous St. Valentine's Day massacre, the Corsairs suffered a disastrous first engagement. 9 American aircraft were lost, including 2 Corsairs, multiple P-38 Lightnings, P-40 Warhawks, and bombers, while the Japanese defenders lost just 1 0 fighter. The 9-1 loss ratio in favor of Japan was so severe that daylight bombing missions to Bougainville were suspended for tactical reassessment. This engagement underscored the fact that superior technology alone could not guarantee victory. Tactics, experience, and proper deployment were equally crucial. American pilots quickly adapted, realizing that the Corsairs' strengths were not in dogfighting, but in what became known as boom and zoom tactics. The Corsair couldn't outturn a Zero in slow-speed maneuvers, but it could outdive, outclimb, and outrun any Japanese fighter. Successful tactics meant maintaining speed and altitude advantage, diving on enemy aircraft, firing and using superior speed to disengage before the enemy could respond. On May 13, 1943, Second Lieutenant Kenneth A. Walsh of VMF 124 became the first Corsair ace by mastering these tactics, ultimately achieving 21 victories. As the war progressed in 1943 and 1944, the Corsair's reputation soared. Marine squadrons in the Solomon Islands, flying from makeshift coral airstrips, used the aircraft's ruggedness to devastating effect. The Corsair proved capable of absorbing battle damage that would have destroyed lighter Japanese fighters. Its 650 caliber Browning machine guns, 4 inboard guns with 400 rounds each, and 2 outboard guns with 375 rounds each, totaling 2,350 rounds, provided overwhelming firepower. Later variants like the F4U replaced the machine guns with 4 20mm cannons, though many pilots still preferred the reliability and ammunition capacity of the 50 caliber weapons. The Corsair's versatility extended beyond air combat. By mid-1944, Corsairs routinely carried external ordnance, such as 1,000 lb bombs on centerline and wing racks, 8 5-inch high-velocity aircraft rockets, or napalm canisters. This fighter-bomber capability proved invaluable during amphibious operations. During the Okinawa campaign in 1945, Corsairs flew thousands of ground attack sorties, earning the nickname Angels of Okinawa from grateful infantrymen. What Japanese pilots encountered in combat represented only part of the Corsair's story. From the cockpit of a Zero or another Japanese fighter, the Corsair appeared faster, stronger, and more resilient. However, understanding the engineering and manufacturing techniques behind these advantages required physical examination of the aircraft itself. Japan's ability to conduct such technical analysis was centered around 2 facilities: the Yokosuka Naval Air Technical Arsenal south of Tokyo and the Army Aviation Technical Research Institute at Tachikawa. Throughout the war, these organizations had been meticulously studying captured Allied aircraft, recovering examples from battlefields across the Pacific. Their efforts had provided valuable intelligence regarding American capabilities, but most of the recovered planes were damaged or incomplete wrecks salvaged from crash sites. The arrival of an intact, operational American frontline fighter was an extraordinary opportunity for the Japanese. The Japanese Navy's Yokosuka facility had been conducting technical research since April 1, 1932, when it was reorganized as the Kaigun Kokusho Naval Air Arsenal. By World War II, Yokosuka employed thousands of engineers, designers, and technicians. The facility was responsible for designing numerous Japanese naval aircraft, although the actual production was contracted to companies like Aichi, Nakajima, and Mitsubishi. Yokosuka's engineers were seasoned professionals, well-versed in aircraft design at the highest level. When a salvaged Corsair arrived at Yokosuka in early 1945, it was one of the most modern American fighters recovered in relatively intact condition. Although the aircraft had suffered some water damage during its forced landing, the core structure remained largely intact. Recovery teams had worked hard to prevent the plane from sinking completely, and the fighter was transported to Yokosuka's secure technical area for a thorough examination. The initial assessment focused on the overall condition of the aircraft. Despite the saltwater immersion, much of the Corsair was still in good condition. The massive Pratt & Whitney engine required complete disassembly and cleaning, but the airframe showed no signs of combat damage, which was crucial. Many previous Allied aircraft captures had involved heavily damaged planes, making it difficult to distinguish between design features and battle damage. Japanese specialists began their examination by systematically photographing and measuring every dimension of the aircraft. The wingspan was 40 feet 11.7 inches, the length was 33 feet 4 inches, and the height was 15 feet with the wings extended, or 16 feet 2.3 inches when the wings were folded for carrier storage. The inverted gull wing configuration immediately caught the attention of the Japanese engineers. They understood the aerodynamic and structural benefits of this design, but also realized the manufacturing complexity it entailed. Creating the compound curves and maintaining precise angles required advanced tooling and quality control, something beyond the capabilities of most Japanese factories at that stage of the war. The examination uncovered something particularly surprising to the technical team. Despite the Corsair's advanced design, some parts of its outer wing surfaces were covered with fabric instead of metal. This fabric covering extended to the areas after the main wing spar and armament bays, as well as the control surfaces, including ailerons, elevators, and rudder. At first, Japanese aviation specialists found this puzzling, as by 1944 to 1945, most modern fighters had switched to all-metal construction. Further analysis revealed a deliberate design choice from the aircraft's 1938 to 1940 development period. The fabric reduced weight where structural loads were minimal, conserving aluminum for the critical load-bearing components. The fabric was specially treated to provide sufficient strength and weatherproofing, while weighing much less than metal skinning. This demonstrated a sophisticated understanding of resource allocation for optimal performance. Disassembling the wing structure revealed construction methods that impressed the Japanese technical team but also raised concerns. The main wing spar, which was a critical structural component, the main wing spar, which carried flight loads, was a massive forging of exceptional quality. American metallurgy had produced aluminum alloy forgings with strength characteristics that Japanese facilities struggled to replicate. The spar's dimensions and load-bearing capacity far exceeded those found in comparable Japanese fighters. This component alone highlighted a fundamental difference. American industry was capable of producing large, complex forgings with consistent quality. Meanwhile, Japanese manufacturers increasingly relied on built-up structures assembled from smaller components. The internal structure of the wing demonstrated a similar level of sophistication. Ribs, stamped from aluminum sheet, showed remarkable precision and consistency. Each rib was virtually identical to the next, indicating manufacturing processes with tight quality control. As the war progressed, Japanese aircraft production struggled with consistency, with individual planes showing variations in component quality. Attention then turned to the Corsair's armament installation. 6 Browning AN-M2 .50 caliber machine guns mounted in the wings provided formidable firepower. The installation was compact, reliable, and designed for easy maintenance. What impressed Japanese examiners was not only the firepower, but the completeness of the system. Ammunition boxes, feed systems, spent cartridge ejection, and charging mechanisms were all engineered to work seamlessly together. The guns themselves were examples of precision manufacturing. American ordnance production had reached levels of reliability that Japanese industry envied. The Browning M2 machine gun was a mature design perfected over decades, manufactured by the millions with extraordinary consistency. Japanese technicians examining these weapons recognized manufacturing techniques and quality standards that their own factories could not consistently achieve. The discovery of 150 pounds of armor plate protecting the cockpit, along with a 1.5-inch thick bullet-resistant glass panel behind the windscreen, further reinforced the impressions of American design philosophy. Japanese fighters had largely abandoned heavy armor protection in favor of lighter weight and better maneuverability. The early success of the Zero seemed to validate this approach. But as American fighters became more powerful and better armed, the lack of protection proved to be fatal. The Corsair demonstrated that it was possible to incorporate substantial protective armor without sacrificing performance. Thanks to the massive power of the R2800 engine, the Pratt & Whitney R2800 Double Wasp, dominated the technical examination. The 18 cylinders arranged in 2 rows of 9, displacing 2,800 cubic inches and producing over 2,000 horsepower, represented the peak of American aero engine development. Japanese engineers had encountered this engine before in captured aircraft, but they had never had access to an example in relatively good condition for thorough analysis. The engine's construction revealed manufacturing capabilities that seemed almost incomprehensible. The cylinders were precisely machined with tolerances measured in thousandths of an inch. Pistons, connecting rods, and crankshaft components displayed surface finishes and dimensional accuracy that Japanese engine manufacturers struggled to achieve. The 2-stage supercharger system, designed to maintain power at high altitudes, incorporated complex internal passages and precisely fitted rotating components. Japanese attempts to develop comparable engines had yet to match the level of refinement and performance found in the R2800. Supercharger systems in Japanese aircraft had largely failed due to manufacturing limitations. What stood out most was the engine's reliability and power output. American radial engines, like the R2800, routinely produced their rated horsepower for hundreds of hours between overhauls. In contrast, Japanese engines, even new models, often failed to achieve their theoretical power ratings and required frequent maintenance. The R2800's consistent performance resulted from superior metallurgy, better lubricants, more precise manufacturing, and advanced quality control. The propeller system was equally revealing. The Hamilton Standard hydrostatic propeller, with its 13 ft4 in diameter and variable pitch capability, represented advanced aerodynamic design and hydraulic control systems. While Japanese engineers understood propeller theory, they lacked the facilities to produce large propellers with the required precision. The examination of systems throughout the aircraft revealed consistent patterns. The landing gear mechanism, though complex, was precisely manufactured. The cockpit instrument panel had a comprehensive array of gauges and controls, surpassing anything found in Japanese fighters. The fuel system used self-sealing tanks with multiple rubber compound layers that swelled when punctured, preventing catastrophic fuel loss, a technology Japanese aircraft largely lacked. The electrical system powered extensive equipment through high-quality wiring, properly insulated and organized. What stood out most was the overall quality of materials and manufacturing. Every component, from major structural elements to small fasteners, showed consistent quality. Aluminum alloys had uniform properties, steels were heat-treated properly, and surface finishes were smooth and professional. The aircraft felt substantial, well-built, and made to last. This overall quality was in stark contrast to Japanese aircraft production in 1945. Wartime shortages had led to increasing use of substitute materials. The quality of aluminum had deteriorated, skilled workers had been conscripted, and factories operated under constant threat of American air raids. Quality control suffered as production schedules prioritized quantity over quality. The examination of the captured Corsair occurred at a time when Japan was facing imminent defeat. American B-29 bombers were systematically destroying Japanese cities. The Navy had been shattered at Leyte Gulf, the Philippines had been liberated, Iwo Jima had fallen, and Okinawa was under assault. In this desperate context, the Corsair examination took on somber significance. It was no longer about intelligence gathering for future victories, but a final reckoning with technological reality. Japanese engineers at Yokosuka and Tachikawa wrote technical reports documenting their findings. These reports detailed measurements, described manufacturing techniques, and offered assessments of American capabilities. While professional in tone, the reports could not hide the underlying implications. In nearly every category examined, American technology exceeded Japanese capabilities. The gap was not small or easily closed. It represented years of industrial development, massive investments in research, advanced tooling, sophisticated supply chains, and resources Japan simply did not have. By the war's end in August 1945, at least 2 Corsairs had been captured by Japanese forces. Evidence suggests that technical personnel made serious efforts to repair at least one aircraft, as photographs show captured Corsairs with patched wings and fuselages. Whether actual flight testing occurred remains uncertain, but the repair attempts indicated a genuine effort to make the aircraft operational. When American occupation forces arrived at Yokosuka Naval Air Technical Arsenal in September 1945, they discovered extensive evidence of Japan's technical intelligence efforts. Captured Allied aircraft were scattered throughout the facility, and technical reports, drawings, and photographs documented Japanese attempts to understand Allied technology. American intelligence officers quickly recognized the value of these materials for assessing what Japan had learned. The Japanese examination of the F4U Corsair symbolizes more than just technical intelligence. It highlights the vast technological gap between American and Japanese aviation by the end of the war. When the Corsair entered combat in early 1943, Japanese pilots in Zero fighters could still compete effectively, relying on superior tactics and pilot skill. By 1945, however, even experienced Japanese pilots flying more modern aircraft had little chance against well-flown Corsairs. The aircraft's technological advantages, combined with overwhelming American numerical superiority and better pilot training, created nearly insurmountable odds. The Corsair achieved an official kill ratio of 11.1 against Japanese aircraft. American pilots flying Corsairs shot down 2,140 Japanese aircraft while losing only 189. Corsairs to enemy action during World War II. These figures not only reflected the Corsair's technological superiority but also the entire American war machine's advantages: better training, superior logistics, overwhelming production capacity, and advanced technology at every level. Japanese engineers examining the captured Corsair understood the significance of these factors. They could measure the performance gap, analyze the manufacturing differences, and calculate the resource disparities. Their reports documenting these findings stand as an acknowledgement of Japan's failed attempt to match American industrial might. The Corsair itself went on to serve long beyond World War II. It fought in the Korean War from 1950 to 1953, where it proved effective in ground attack and close air support roles, even as jet fighters took over air superiority missions. Foreign air forces, including France, used the Corsair in colonial conflicts into the 1960s. The last combat missions by Corsairs occurred in July 1969 during the brief Soccer War between Honduras and El Salvador. On July 17, 1969, Honduran Captain Fernando Stowe, flying an F4U-5, shot down 3 Salvadoran aircraft, including 2 FG-1D Corsairs, marking the final combat victories for the type. From its first flight in 1940 to its final combat missions nearly 3 decades later, The Corsair proved one of aviation history's most successful and enduring fighter designs. For Japan, the encounter with the Corsair was part of a broader reckoning with technological reality during the American occupation. Japanese engineers and scientists, who had struggled with material shortages and industrial limitations during the war, now worked with American occupation authorities to rebuild Japanese industry. The lessons learned from examining American technology, including the Corsair, influenced post-war Japanese manufacturing philosophy. The emphasis on quality, precision manufacturing, and continuous improvement that characterizes modern Japanese industry has roots in the hard lessons learned when Japanese engineers examined what American industry could produce. The Corsair, recovered in early 1945, represented more than just a downed fighter. It was evidence of engineering excellence and manufacturing sophistication that Japanese aviation had been striving for throughout the war. The lessons it taught came too late to alter the war's outcome, but they helped shape the peace that followed. By examining this American fighter, Japanese engineers confronted the full magnitude of the challenge they had faced. They had fought with courage and skill, but courage and skill alone could not overcome the technological and industrial advantages their opponents possessed. The story ends not with triumph, but with acknowledgement. Japanese technical reports on the Corsair, discovered by American occupation forces and now housed in archives, serve as silent witnesses to a moment when one nation's engineers fully understood the capabilities of another nation. The Corsair they studied has long since disappeared, likely scrapped during the chaotic post-war period. But its legacy endures in the lessons it imparted about what technology, when properly applied with adequate resources and sophisticated manufacturing, could achieve. Japanese aviation would rise again in the post-war era, but never again would Japanese engineers underestimate the capabilities of their American counterparts when given the industrial capacity, scientific knowledge, and resources to fully realize their designs. The examination of the F4U Corsair by Japanese technical personnel in 1945 stands as a watershed, a moment. The point when Japan's aviation establishment truly grasped the technological chasm that had opened during the war. It was a lesson that was written not in propaganda or combat reports, but in aluminum alloys, precision forgings, and manufacturing tolerances that spoke louder than any words could about the true nature of American industrial power.